Okay, stream is good.
Awesome. Let's kick it off. Welcome everybody to, I think this is probably the 5th HackFS event before kickoff. We've been doing a series of workshops related to Filecoin, libp2p, basically the whole tech stack this week, just to get people familiar with these new, sorry, I just got distracted. Getting people familiar with new stuff if they're not familiar with the Filecoin ecosystem. And today we are really excited to have Jacob Heun with us. He will be giving an overview of centralized messaging and libp2p. He is the JS libp2p tech lead at Filecoin. And like I said, we're very happy that he was able to join us today, and he's going to share some of his expertise on this topic. Before I pass it over to him to start off, a few things. Like I said, make sure you've staked for HackFS. This is how we ensure that people are really committed for the event, and we want to make sure we're supporting people who are committed. It's only 30 DAI, and you get it back after the end of the event. So please make sure to do that before Monday. If you have any issues, DM anybody from the team. We will look into it for you. We've got one more event tonight after this, which is the brainstorm session, whereas the previous events this week were more workshop focused, technical. This brainstorm session is going to be a little more open-ended. Come chat about ideas, 8 p.m. Eastern tonight. Hopefully that's not too late for some of you, but looks like we're going to have a good showing. What else? Oh, of course, the kickoff is on Monday at 12 p.m. Eastern. Hopefully everybody gets used to translating from Eastern to their local time if you're not already, but that's just what we've chosen to get people on the same page. And one other thing we like to do in these events before kind of getting into the swing of it is we play a game that I invent every time. This time we're going to do the one we did yesterday. You turn on your videos. Let's see, Andrew, I need you to count. Since you and Jacob have colored shirts on, that's what we're going to count. Colored shirts, and I will be team monochromatic. All right, let's see how many black shirts we've got. Andrew and Jacob, please count the colored shirts. Let's see who wins. 1, 2. Oh, wait, no, Nazareno, you've got some stripes, man. I don't know. I don't know about that. 1, 2, 3, 4, 5, 6.
We've only got 7, like 2 colored shirts.
8. I thought it was going to be more balanced.
Bring some color into your life.
Yeah, come on, people. No, wait, no, I'm team monochrome. Sorry. I failed to account for striped shirts, so we'll have to consider that for next time. So I think the black shirts win this time. Last time it was a tie. So go team dark shirts. And with that, Jacob, we're done with the games. The floor is yours. Give us a little intro about what you do, what you have done, and what you're going to talk about.
Yeah, hi everybody. As Trent said, I'm Jacob Heun. I have been working with Protocol Labs for a little over 2 years now, primarily focused on the JS side of libp2p and JS IPFS. You'll also see me popping up in Go libp2p and Go IPFS from time to time, but primarily on the JS side of things and helping out with like release management and release planning. So if you really, really want things for libp2p and IPFS, I am a great person to throw requests at. So feel free to do that. And yeah, so today what we're going to be doing is kind of giving you a brief overview of decentralized messaging. We'll kind of talk a little bit about like, how is that different from centralized and how is it different from distributed, which is the thing ideally we'd like to get to. And we'll talk about how to do that in libp2p. Today, we're going to be going through the JS implementation of libp2p, specifically in Node. But for those of you who you can either follow along there, the workshop is kind of broken down into chapters to kind of step through, where each subsequent chapter has solution code already in place. So if you get lost partway through, you can just change into the next directory and get that running. And if you aren't in a coding mood today, there is a browser version in the repo, and that is up on the gateway of IPFS. So you can chat to your heart's content This is a very, very basic chat application in React. So if you want to use a nice chat application, maybe use Matrix and not this, but we'll play around with this today. All right, so I'm going to go ahead and share my screen and we will jump into it. If you guys have questions along the way, feel free to shoot them into Zoom. I'll do my best to answer them along the way. Once I reorganize chat because Zoom is mean.
Do you have a
Okay, yeah, so go ahead and pop stuff into Zoom as we go. Otherwise, we're just going to go through this, and then I'll leave space at the end if you have like broader, more in-depth questions. So here is the just the README for the workshop. So if you want to pull that down, feel free to do that. And we will get started. If you haven't pulled it down already, here is what the web chat app looks like. You can see this is a very depictive picture of what the internet and libp2p looks like today, with this green one being a Node.js node, and the not very well connected browser node is in purple. But let's go ahead and jump in and start talking through this. So, yeah, again, code for today is up there. The branch is HackFS if you want to follow along there. In the main branch, we're also kind of updating this along the way as we release new versions of libp2p. So the repo is just a good place to come back to if you ever want to see how we're going through and updating from like 0.27 to 0.28 and beyond. So talking a little bit about centralized, decentralized, distributed, like right now we're kind of in this era where we're pushing more towards decentralized, but we've been in a centralized structure for so long where these center nodes are like heavily controlled by a few very large corporations like Google and Amazon. And there are like intrinsic problems with this that we have like, they're the places where all the data goes, so they can house as much as they want. They keep that. We have GDPR in places like Europe, but in the US, they kind of have freedom to pull all that information. Another consequence of that is that it's very easy to censor single points, and that becomes difficult for people living in China or Turkey, in places that are kind of restricting those endpoints. So ultimately what we want to do is we want to get to a point where we're able to develop a full peer-to-peer network. And this is really this distributed side of things, this full mesh looking infrastructure. The problem with that is that talking directly peer-to-peer is very difficult. Building a distributed system is very difficult in today's technology setup, especially when we look at like browsers and being able to connect to them. And so kind of where we're at right now is this middle ground of we're building a decentralized network in Web3 on our way to getting fully distributed. And we do this thing with like rendezvous servers and WebRTC, which we'll talk a bit about today, with circuit relay nodes, things like that, where we can like have these center points where lots of people can connect to and then create, you know, peer-to-peer ecosystems from there. So not quite what we want, but it's a good stepping stone to get there. So how does libp2p play a role in this? So libp2p is the networking stack that IPFS, Filecoin, Ethereum 2, and a few other ecosystems are building on. And the reason for this is libp2p is designed to be a modular system of protocols. As we get better support for distributed systems, and as the internet and our infrastructure evolves over time, like we need to make sure that we're building a networking layer that's going to be able to adapt to those changes. And so this is really what libp2p is trying to do, is create that foundational layer so that people can build awesome applications on top of it. So getting down into the bits of libp2p, the first thing we need to look at is like transports, because transports are the foundational layer that libp2p uses to connect to other nodes on the network. And there's a wide variety of them, and they're continuing to grow as like technology grows, and as more and more people are joining the libp2p ecosystem. They're starting to develop, more interesting and neat ways of passing that data around. So each transport comes with its benefits and its drawbacks. Here's a very basic table of where things are at today. This only includes Node, Go, and Rust, but we have currently to date 7 implementations of libp2p. We also have like Java, Python, C++, and NIM. And so like this ecosystem is growing, and it's making it easier and easier to develop libp2p across different platforms. So today what we want to look at, because we're building this in JavaScript, we're building a node only application right now, but we also want to make sure that this chat app that we're all in, we have the ability to also connect to the browser. So looking at WebSockets and WebRTC. So talking through a little bit more of these transports, like TCP is a very basic transport that a lot of the servers are using. So Go uses it, Rust uses it, and Node uses it. So this is a pretty prevalent, widely supported transport, but it does have its drawbacks. Like we can't talk to browsers. It can't run in browsers. WebSockets is nice because like it's widely supported in the implementations, and it allows browser nodes to talk to server nodes. The big drawback here is that WebSockets in the browser have to have an SSL certificate at the node that they're trying to talk to. So if you run a server in Node or in Go, you have to put an SSL certificate in front of it and a domain, because currently, at this point in time, SSL certificates don't work for IP addresses. That might be a thing in the not too distant future, but that's currently a limitation, which makes this very painful to make a peer-to-peer network explicit on that. Yeah. Cool. And then WebRTC. WebRTC is really nice. We currently don't have, there is working support for it in Go. It's not quite there yet. We're probably going to be looking at reevaluating that, because one of the nice things about WebRTC is it has built-in hole punching. And hole punching is the thing that lets us talk from browser directly to browser. So like using this chat app in Chrome or whatever browser you're using, like we're connecting over a rendezvous server, and then we're doing hole punching to actually talk directly browser to browser. So we don't actually go through a relay server, which is really, really nice. It's a very efficient form of communication. And then we're working on an evolving quick transport. So the RFC for quick, it's still in progress, but it's being finalized. And so we have the latest RFC is implemented in Go, and we've actually been working with the Node.js team to get support in Node.js. So that is coming, hopefully in the not too distant future. I think it's already experimental in Node 12, or at least a fork of it, so you can play around with it there. I think we have a very rudimentary version of that in Node, but not quite there yet. So looking at what we're building today, we said, okay, let's look at Node because that's what we're running. And then we want to make sure that we're able to talk to browsers. So what we're going to do is we're going to add TCP, which is going to let us talk to things like DHT servers and other server nodes. WebSockets is going to let us talk to any bootstrap nodes that are on the network, because all of the bootstrap nodes that the Protocol Labs team supports, all of our libp2p bootstrap nodes, those all have SSL in front of them. So we can totally get that out of the box and connect to the network. And then WebRTC we're going to use so we can actually talk directly to one another over browsers. So over this, we're going to kind of skip through some of the chapters just so I can get this done in roughly 60 minutes. And so we're going to go through several of these concepts along the way. And then when we get to the basic setup for libp2p, we'll jump into the code and see what that looks like. And then from there, we'll move on. Even for localhost. Localhost is actually a secure domain. So when you're testing locally, you don't have to worry about it. You can connect to your localhost server. So Now that we've selected our transports and we know what we're going to use, what we need to do is look at like, okay, how do I contact you on the network? If you think about things like today, us as people, we have telephone addresses, mobile phone addresses, email addresses, postal addresses, Telegram accounts. Like we have all of these various ways to contact people, and there's not a clean way to do that. If you were to fill out a form with all of your contact information, like you would have to have like a ton of different fields formatted differently, and those change over time, and that becomes like very, very painful to represent. And what we want to do as libp2p is make sure that that is like somewhat future-proof, that we can evolve these addresses over time that have a like singular structure. So we don't have to worry about that. We can just derive addresses from that. So what multi-addrs do, or multi-addresses, they allow us to compose flexible addresses in a path-like structure when they're string representation. So they also tell us a ton about the host that we're going to contact, because we need that information. So we're going to step through a few multi-addrs here because they can be a bit difficult to consume. But the first one we have here is like your very basic listen address that you'll see in IPFS. And what it's saying is, I'm looking for an IP4 address at this IP address, localhost, and I want to connect over TCP. So this is defining our transport, and then we're going to connect on port 4001. So fairly straightforward. The next one is almost the same sans the port change, except we have WS at the end. And what this is telling us is we're going to run a WebSocket connection over a TCP transport, because WebSockets traditionally run over TCP connections. Looking into some much more verbose, we've gone from the simple thing to the much more complicated thing. But this is one of the servers that we're going to look at connecting to. Actually, today we'll be connecting to one of the sub-servers of that main domain. But here we have a DNS4. So we're running a DNS domain address, which means we are going to need to do a IP DNS lookup. So this will probably automatically happens in Node, but for things like the browser, we actually have to do like resolution, and that becomes painful because we actually don't have a way to do that in the browser without doing DNS over HTTP, which is kind of annoying. But so what we want to do is we want to resolve the WebRTC star discovery.libp2p.io address. That is a TCP connection that's running on a secure port of, secure port of 443. And then you'll notice instead of WS, this is WSS, which indicates that this is a WebSocket secure connection. This is required for browsers, but things like Go and Node don't actually require SSL certificates, so you can actually make secure connections just over WebSockets, which is nice because we can just fall back to libp2p decryption. And at the very end of this is the thing that tells us this is a WebRTC star connection. And so this is a WebRTC rendezvous server, which is going to allow us to negotiate WebRTC hole punching. So the next thing here is similar to TCP, except we're going to be running a UDP connection. So this is going to be packet-based switching instead of TCP. And then that's going to be running on 4001. Again, this is like your default IPFS implementation if you have quick enabled in Go IPFS. And then that's running the quick transport. And then we see here that we actually get this P2P. Like in the past, if you've been working with IPFS for a while, this was typically IPFS. But because like libp2p is for many more applications than that, we've changed that to just the P2P protocol. What that indicates is there's a pure ID that's about to happen. In this instance, it's a truncated QM relay is the peer ID. And at the very end of this, we see that this is a P2P circuit. So when the switch goes to look at this, it says, okay, I am going to make a relayed connection to this peer. So I'm going to dial this peer over quick and then negotiate. So this was what you might use for a listening address if you wanted to listen over this relay. Okay. So once we have that, really what we need to do is like, okay, we have some understanding of, hang on, can you talk a little bit more about the circuit and how it might be shared? Yeah, we can look at that we'll touch base back at that at the end. Please remind me, ready. So adding the multi-adder, once we do that, once we've figured out our multi-adders, we'll go through this in a little bit and to look at like, okay, what does this setup actually look like? We need to actually specify what are our listen addresses. We might want to change what our announce addresses are. So for example, if you are running a server and you want to put a domain name in front of it, like you want to announce addresses that you're not listening on, you want to announce that domain address. And we'll kind of look at some of what that looks like. So the next thing we need to do for our base connection is look at like connection reusability. So in libp2p, there's a variety of protocols. There's application level protocols, pub sub messages, DHT queries, circuit relay is a protocol, file exchanging like IPFS and Filecoin, and then the chat protocol that we're building today, at least the first part of it. And then like if you build something new on top of libp2p at HackFS, like you're going to need to create your own protocol for that. And so like, how do we handle this with singular connections to other nodes? How do we handle all of these things? We don't want to create new connections for each of those. We want to be able to reuse that. And so if you kind of think about this, like the concept of, if you've ever like heard about or seen a tin can phone, basically the idea of I have, 2 tin cans and I punch a hole through it and have just a string running through a top string. You can speak through that and that will transfer information. But if you try to have multiple people talking into it at the same time, like you're not going to get anything out the other end. It's just going to be garbled. And so what we want to do is to be able to take this like very P2P connection, and we want to be able to do multiple virtual connections over it. So it's kind of like this idea of we're creating virtual strings across our tin can phone so that we can run each protocol on those streams. And we'll look at a little bit more what that looks like. So this is called stream multiplexing in libp2p, and multiplexing is a concept that actually dates back to early days of like telephony. In telephone lines, what they actually will multiplex multiple conversation over different frequencies. And that's how they handle it in telephone. TCP connections do it over multiple ports, so you're not getting multiple connections per port. You have singular connection that will multiplex over multiple ports to the applications that are receiving that. And then for MPlex, which is it's not the only multiplexer for libp2p. We have like Yamux and Quick has a built-in multiplexer, but MPlex has the widest support right now because it's relatively easy to build compared to some of these other things. So once we have that, right, we have our transports, we have our multi-adders for people, so we're able to connect to them. We're able to multiplex the connection so we can have multiple conversations over a single connection. The next thing we need to do is encrypt this, because we don't want this data just free flying over the internet in plain text. That's not good life for anybody. So what we want to do is encrypt that. So when selecting our encryption protocol, we need to think about a few things. So our current supported protocols in the various languages are TLS 1.3, which is used right now by default for Go. And then noise is going to be the default security transport, I believe, for ETH2. And the reason for this is noise is a framework for building security protocols, and it's actually pretty easy to implement, well, relatively easy to implement in the various languages. Like TLS, we have to deal in like Node. We need a TLS 1.3 implementation working in Node.js before we can do that. And then we're blocked on the browser because the browser doesn't have TLS 1.3 support. With noise, we can write all those protocols and then we can just handle that exchange. And we have full support already in JavaScript and Go, and we're working on getting those downstream in the other implementations, which are very close. Then again, Quick has a built-in TLS security. And SecIO, you'll probably see that around. That was originally developed as a stopgap solution for TLS 1.2, not being able to do self-signed certs. And so SecIO will phasing away as we have these new security transports in place. And here's just a quick capture of Wireshark. I don't want to bore you with all of the details here, the too nitty gritty, but what you'll see here in the top right is really like, once you've encrypted a connection, you'll see that the thing that gets exposed is the original multi-stream handshake. So we go in and say, hi, do you speak this multi-stream protocol? And then we'll reply back with, yes, I do. And then we select from there crypto. And as soon as we agree on crypto, in this case, SecIO, everything is immediately moved into crypto handshakes and encryption. So everything's secure. If we did this in plain text, you would see a variety of protocols being negotiated. We can table the key exchange one for the end. So base configuration, like we've talked about a lot of things. This is a lot to absorb. Let's kind of like jump into the code here and get a look at what exactly this looks like. So if you are following along in the code, we're just going to jump into chapter 4 protocol. Okay. So just kind of stepping through the setup here. And if you follow along at the beginning, start at like chapter 1, it'll kind of guide you through requiring some of these things. But here's the baseline of setting up multiplexing and encryption. So right at the top, right, we have our transports that we talked about. We've got libp2p TCP, we have libp2p WebSockets, and WebRTC star. The next thing we need, because Node.js doesn't actually have support for WebRTC out of the box, so we need to custom install that module. In the browser, in most browsers, we get WebRTC for free. It's already there, but we need to bring it with us when we're building Node. The next thing is our multi-adder module that's going to let us do all the multi-adder creation. From there, Mplex. Here we're using both noise and SecIO is more of like a fallback. So what we want to do is we want to default to noise as that's going to be the de facto going forward eventually. And then SecIO is kind of a fallback. And so that will allow us to talk to legacy nodes on the network who are still only speaking SecIO and haven't had a chance to upgrade to noise, which is really important to be able to kind of like have that gap of letting the network upgrade. From there, we'll look at the chat protocol in a second, but this is just a file that pulls in like a very, very rudimentary chat protocol. And then libp2p core, which is what we're going to plug everything into. So here we just have a main asynchronous function because we need to do some awaits in here, because a lot of the code is promise-based. We moved away from callbacks about a year ago. And so in here, what we want to do is we need to create the libp2p node. So as there is a convenience constructor, because oftentimes the construction needs to happen asynchronously, it's promise-based, because we might need to generate keys or peer IDs if you haven't specified one in advance. So from there, we can actually select our addresses. And here we talked about creating the listen addresses specifically. Like we want to listen on a wildcard. So what this means right here, IP4000 TCP, is I want to listen locally on any port. Just give me an open port. I really don't care what it is. And then later on, we can announce that to the network, and libp2p will handle that automatically. And then the next thing we want to do is we want to make sure that we have our WebSocket connection as well. And so we're adding the listen address. Same thing, it's going to listen wildcard, find any port that it can, and listen. In things like IPFS, like these are going to be hard-coded. So you've got like 4,000, I think the other one's 4,002. And the reason for this is like, you can predict what those ports are going to be on. If you want to set up like port forwarding on your router at home, you can do that instead of port sharing, and actually like, it's easier to plan that way if you don't have like UPnP set up on your home router. And then the last address here is the WebRTC transport. And that's the multi-adder that we kind of showcased, although this is a little bit different. This is one of the WebRTC addresses. So if you go to the WebRTC repo, we've got a list of a couple servers that we now host so that you can troubleshoot, you can play around with it, and then you can always run your own WebRTC star server. From there, we get into actually specifying the configuration. So going in and saying, okay, the transport, I want to pass in TCP, WebSockets, and WebRTC star. These are also going to be kind of in order of preference. And so in this instance, if the peer that we want to dial has TCP addresses, we're going to try to dial those first in order. We do parallel dials. I believe it's up to 8 by default that we'll try at any one time, but any TCP ones will be prioritized than WebSocket and WebRTC, and usually because these are like the more efficient ways of connecting. So we want to try to prioritize those performance. So from there, we look at the stream muxer, which in this instance is Mplex. And then connection encryption, again, noise and SecIO, this is preference-based. So we're going to attempt, when we're connecting to somebody, we're going to attempt to negotiate noise first. And then if that fails, we'll try SecIO. This does have a consequence of like it costs a round trip. So there is some latency there if we're trying to talk to like legacy nodes. But we get the advantage of like slowly upgrading the network over time. Typically, if we're rolling out a new transport, like right now in JS-IPFS and in Go IPFS, these are switched. So we'll actually do SecIO first because like I upgraded first. I don't want to immediately take the performance of a round trip. So I'm going to upgrade, add support, and then I'm going to let the network upgrade for a little while before I switch those priorities. And then eventually we'll just decommission noise. But for this, we're going to leave noise as the preferred one. This thing here is a little bit kludgy, and we're going to be working on making the transport configuration, just configuration in general, better in the future. But all this is, it's kind of a hack of saying, okay, I want to, when we construct the transport, because libp2p needs to inject itself into transports on creation, I also want to pass it these additional properties. And so what we do here is look at WebRTC star, and we get its symbol string tag. We can't use like a constructor name or anything like this because when you go in a browser and you bundle it, it totally obfuscates the name of the constructor, and that's just going to cause you nightmares. So we have this kind of like convenience constructor, and in the future that will be easier to do. But all we're doing here is saying that WebRTC module that we included, we want to pass that in to the WebRTC transport so we can leverage that. Then from there, that's the basic creation. So we don't really have discovery built in right now. There's nothing specified. We'll talk about that a bit more in a minute. However, because WebRTC star is a rendezvous transport, we will automatically check for the discovery component. And if it's there, we'll bind to it and we'll immediately listen. So this, you're automatically getting some discovery for free for finding WebRTC star peers, which is pretty nice. From there, what we want to do is, like, this is just a basic thing that as we connect to peers, so listening to the connection manager, anytime a peer is connected, get that connection, and then we can look, let me just shrink this a little bit so you can see. We can look at it and say, okay, whenever I'm connected to a peer, each connection has remote peer on it, which is its peer ID. So we can stringify the implementation of that and we can log it out and we can see what that looks like in a second. And then we'll get into the chat protocol handler a little bit. And then from here, we're just going to start the node. And that's the basic gist of getting everything running. One of the problems this has, this is just some logging information here for the string ID and then the multi-addrs that we're actually listening on, is like this concept of bootstrapping, which we'll talk about in a second with discovery. And right here, we're doing a very crude thing of, we're just going to get the address of one of the bootstrap nodes. And I've hard coded it here and we're just going to dial to that. If you want to like take a look at like some of the servers that we have running, you can actually do a dig. If you have dig on your machine, you can do dig type txt, and then we can actually look at this bootstrap.libp2p.io record. And then we need to preface that with DNS adder. And the reason for this is how the DNS address lookup works. You can just remember that because the DNS adder is at the front. It just needs an underscore. So when we dig that information, we're going to get back text records. So libp2p.bootstrap.io is a kind of a round robin gateway that houses all of these bootstrap nodes. And if you just try to dial bootstrap.libp2p.io, it's going to fail because it has no idea who it's going to talk to. And we currently don't support blind dialing for kind of encryption purposes. So, but you can look at this and see, okay, we've got a bunch of DNS adders back. And so what we ended up doing is just selecting one of these. And then from there, you look at it, it's a DNS adder again. So you can additionally resolve that, and those individual ones are going to resolve to IP addresses. But for the sake of this, we're just going to target one of the bootstrap nodes. And then we're just going to dial it from there. So if we run that again, and we say we're in chapter 4, so if I do node 04, I'm in root, node 04 protocol index, and I can run that. So we're going to see our peer ID, and we are listening on the following addresses. So we see the wildcard 0 got replaced with our external port. And then so we've got a couple TCP addresses. These are all local gateway, local host and local gateway, and then our WebRTC star server. And then you can just see as we've bootstrapped and we've connected over WebRTC, we're getting that free discovery, right? There's no other discovery protocol in place. It's just WebRTC star. And if you're looking at the browser, you probably see like a lot of like spam updates going on with the nodes. Right now, we are connected only to WebRTCs. We're connected to 2 peers. We're connected to the Bootstrap server, which is over our TCP connection. This is the one we manually dialed. And then WebRTC star are all of our other connections. So all these other ones are going to be WebRTC star connections. So I'll go ahead and shut that down for now. And then we'll take a look. So this is the base configuration, right? We're connected to the network. We're connected to peers. We've got browser peers. We've got node peers. This is great. So the next thing we probably want to look at doing is like, let's get an actual protocol in place so that we can do something with this. So what are protocols in libp2p? It's a concept that people usually struggle with a little bit. But what you can kind of think of protocols, like everything in libp2p is basically a protocol. And they're just basically these plain strings. If you've ever messed with a REST endpoint, it's very similar to endpoints in REST. Like these are endpoints in libp2p. So what happens is we register our protocol with a specific thing. Today, we're actually going to use the libp2p chat 100 protocol. And what we're going to do there is we're ultimately going to listen on that. So anytime a new connection comes in, a stream opens, that connection is going to come in, and that protocol is going to be at the front of it. And so we're going to pick it up and say, okay, libp2p chat, yes, I handle that protocol, or I don't handle the protocol. If I handle it, I'm going to take it and I'm going to pass it off to the application handler. So this is going to be our chat protocol code. So then from there, you can send whatever kind of information you want to send over your stream, as long as you know how to deal with it. Kademli for the win. Yeah, we'll get into that a little bit later. And then, so let's actually look at what like creating this protocol looks like. So we'll just pop into this chat protocol. And it's really basic. So we have a handler and then we have a send function. So looking at our protocol, right? This is the chat protocol that we talked about. This is what's going to allow us to chat with anybody else who's doing direct messaging. We'll look at PubSub later for actually doing chat. In the chat application in the browser that's running on the gateway, that's doing PubSub based, not direct messaging. But for getting started, we're going to do direct messaging, because these kind of protocols are very valuable when you want to do like file exchanges, because you don't want to like PubSub that information. You want to get a direct connection before you send a lot of data. So our handler code that we're going to register takes a connection, and then it also has the stream. The connection here is really for convenience to give you that additional information of like, who is the remote peer here? There's a lot of information on the connection. If you want to check out the API docs, we've done a big overhaul of the API docs. Let me try to preview that here. on JS libp2p website. So you can look at that and get a lot more information on things that we expose. And it will include the type, so you can actually go and jump over and look at what the connection is. But we give a lot more information there now, to where you can actually look at stats for the application. What are all the streams open on this connection? Like previously, you couldn't do this in JS and it was a nightmare. So you can get a lot more information there. So, but really what we need is the stream. And that's the thing that, like, okay, when my handler registers, it says, okay, somebody has negotiated the chat protocol, that succeeded, here's the stream with the data on it. So what we want to do is we want to read all that out. And because this is just a very basic string implementation of chat, all we're going to do is we're going to take that incoming message. So this is all like async iterator space, which are pretty nice if you've ever messed with them. But what we're going to do is we're going to pipe everything from stream and we're going to read it out in this function. So we're just going to step over every message that comes through here and we're just going to log that data out. And then we're going to do replies on new streams. So all we're doing here is we're just immediately going to close our write end of it because we only care about reading in that information. On the send side of it, we've just got this basic function set up that we're going to pass the message we want to send and the stream that we want to pipe data over. And so again, we're piping this message array. We could change that to be multiple messages, but for now, just a single message. And we're going to pipe that into the stream, and then we can wait for any responses there. And the reason, like, this is kind of kludgy because, like, nobody's ever going to reply. But if you actually look at like the main branch in libp2p, there's a Bootstrap server in there that you can run, and it will actually just auto reply with some random messages. So we have that set up, but in reality, you don't need to do that. Yeah, and here we're also just, this is logging out the messages that we're actually sending. So you get that, like, the chat log of, hey, I sent this. So if we look at how do we actually register this thing, right? So we've included our chat protocol in the handler. Now we need to do two things. The first thing we need to do is actually register. And so we need to register our handler. So libp2p has a handle method. So we can jump down to this to do. This is add chat handler. So we can just uncomment that. And all we're going to do is pass handle the protocol that we're going to run, which is our chat protocol, and then the handler. And that's it. Like, this is, we're now ready to respond to anything that comes in. But we also need to send some data. So down here, if we go to our next to do, this is just basic handler code that reads from standard in. So what this is going to let us do is actually fire off messages from terminal in Node. So all we're doing is listening to process.standardin, and every time a message gets sent based on a new line return, we're going to get that message in. What we do here is a basic slice, like we trim off the new line, and we're doing a very crude thing here that you should not do in a chat application, is we go through all of our peers in the peer store, we check if it supports the chat protocol, and then we check if we have a connection. If we have a connection, we'll create a new stream, and then we call our chat protocol.send. So this is connection, take an existing connection, call new stream on it. That takes some time because we need to negotiate, like we need to send a round trip to their multiplexer and say, hey, let's do this on Mplex, let's create a new stream, and we want that stream to be the chat protocol. So once we get that back, we can go ahead and send our message over that stream. And then that's it for the code. So if I run that again, now that we've uncommented that, I can go, I can get some chat, and then I can say, hello. Yeah. And so nothing is listening to this right now. So let me pop this open. Node. Oh no. See, this is, oh, I changed it. That's why. This is why we use wildcards. Running all the nodes. 2. Uh-oh, I broke something. What did I break? Should I not run that? Oh, I broke something. Chat protocol handler, did I save? I did save. We don't have much time left. So this is what you do if you get stuck. We open the next chapter and we look at it. And this is going to have our solution code in there. This is a cheat. Lovely cheats. So 0.5 discovery index. If I run that, then I run again over here, node 0.5 index. Yes, I'm spamming all of my peers. And this is where like we're going to look at PubSub. So for sending messages, because it's way more efficient. So now we can see that the chat protocol is working. I don't know what I messed up, but I must have typed something incorrectly. But if you get stuck, CD into the next chapter, and that's going to have everything in there. So all right, that's our base protocol. So now we want to discover probably more peers. Like we have WebRTC star, which is really nice, but we probably want to get more on the internet. I fat fingered. Yeah, I probably did. I've got big chubby fingers. All right. So if we look at peer discovery, like there's a variety of peers that or a variety of discovery mechanisms that we probably want to use. And so Bootstrap is the primary one, right? Like we did the direct dial before, but ideally we probably want multiple Bootstrap lists, and we might want to bootstrap to different parts of the network to avoid either like networks going down. Like we don't want to rely on one. So having a list of nodes that we can initially dial to and bootstrap into the network is valuable. MDNS, we're not going to use that here locally today. What it is local discovery on your home network. Since like this workshop was originally designed for people in place, or people all in one place. But since we all can't be together, we will scrap MDNS. But if you do have infrastructure or an office or like places where multiple peers are going to be connected, MDNS is like a great way to connect with other peers. So it's still very valuable. Downside, it doesn't work in the browser. DHT is also a very, very good way to find peers. One of the limitations there is really like most of the DHT nodes are like TCP only, but we do happen to have a few that run over other transports like WebSockets. So you can actually technically still crawl the DHT, although doing that in a browser is going to be slow because you need to open up a lot of connections. It's usually like, I think in Go IPFS, we're averaging about like 50 dials for a query. That's very expensive when you're trying to do like WebRTC, WebSocket connections. So like you can use it, but it won't work very well. DiskV5, ChainSafe put that together. There's a JavaScript implementation of it by ChainSafe, I believe. And this is for ETH2 network discovery. So that's really nice. It's kind of like a DHT. It uses a DHT to discover peers. So that's also a very nice way to connect. It is UDP only right now. So again, it's not going to work in the browser, but you can use it in Node if you want to. And then rendezvous servers like libWebRTC star signaling servers. And then we're actually building a rendezvous protocol. And what that's going to let you do is actually like ask the rendezvous protocol for like peers that have registered to certain namespaces. So if you build your own chat protocol or your own web application or anything, you'd be able to go to that rendezvous server and ask it directly for like a federated list of people who are registered to that to really kind of short circuit a lot of the initial boot time. And then we do have people who have built some discovery mechanisms in like Bluetooth for local discovery. Web Bluetooth, not quite there yet, but there's another interesting way to find things locally. And looking at like the distributed space, like what we really want to get to that's kind of like looking at the environment that you want to be, is being able to like discover my nodes locally and then grow to the wider network there. So we don't have to depend on, people running centralized bootstrap servers. Like, you can trust us, but you shouldn't trust us. Like, don't do that. Let's make this all like organic and actually make it a peer-to-peer network. That's what we want to see. And then DHT random walk. So in the DHT, the newest version of the DHT in Go IPFS doesn't technically do it's not a random walk, but it's ultimately like a refresh of your routing tables. So if you don't know what a DHT is, it's a distributed hash table. And ultimately it's like a big key value store of peers on your network and then peers who have certain data. And this is kind of how IPFS stores content. If you're looking for content on the IPFS network, like, you're going to look for that CID, you're going to query the DHT for it, and it's going to tell you who has that. Then it's just a matter of connecting to that person to get the data. So, but with that, we can actually use DHT random walk, and we do have support for this in JS, and we are going to run it because it's fun. But that is a great way to just like get to know more peers on the network in addition to actually finding content. So here's kind of how the DHT works if you're not familiar with it. Let's say I want to random walk the DHT. And for simplicity's sake, we're going to say like the DHT IDs are actually like people's names. And so I know Alice and Bob, but I'm looking for Brandon. And so what I'm going to do is I'm going to ask Alice and Bob, like, hey, do you know Brandon? And Alice is going to say, nope, don't know anybody. I don't know anybody close to Brandon. But Bob is going to say, hey, I don't know Brandon, but I know Brenda. And along that process of like making up the ID of Brandon, like Brandon might not even exist. We just say like, hey, yeah, give me somebody called Brandon. We learned about Brenda that way. And so this is kind of how that random walk works, right? It's like just going around a party to meet people and like, do you know Dave? Do you know Dave? Do you know Dave? Like, Dave might not be at the party, like Dave might not exist, but it's a way for you to find new people. So we're going to leverage that. And the best thing to do is to, got to catch them all. Use all of the discovery services. Use as much as you can, because like the more discovery services that you have, it's more tools at your disposal to get connected to nodes and allow other nodes to get connected to you. So we aren't going to use MDNS. Let me scratch that out. But we're going to use Bootstrap, the DHT random walk, and we already have the WebRTC signaling server. So configuring discovery. We are a bit short on time. So what we're going to do is we're just going to look at the pub/sub directory. And again, this is going to have, not you, I want you here.
Hey, Jacob.
Yeah.
It's all right if you go over a bit,
Okay.
because this is recorded. So if there are people following along after and you want to include anything, that's totally fine. We'll be sticking around. Okay,
great. Okay, so looking at, right, we want to do discovery next, configure that. And due to shortness of time, I'll just kind of walk through. But again, CD into the next chapter, pub/sub, and that's going to have all the solution code. So we can ignore pub/sub chat. Here's our old protocol, which we're going to end up getting rid of in favor of pub/sub, but focusing on peer discovery. So here are our things. I lied. MDNS is set up. Haha. So we've got Bootstrap. So rather than dialing that peer, doing a manual dial, we're going to set it up in our Bootstrap list. So we're using the libp2p Bootstrap module. libp2p MDNS for local discovery. So I'm going to be able to discover myself when I run two nodes, but I won't be able to discover you over MDNS. And then we're going to use the DHT for random walk. And so again, our listen addresses are the same. Nothing has changed there. Modules, the only things that we're changing is peer discovery. We're going to add Bootstrap and MDNS. These are exported values from above. And then we are going to include the CAD DHT. So we're running a Kademlia-based implementation of the DHT. But in theory, as long as it meets the API requirements, you could run Coral, you could run other kinds of, like, you can build your own DHT, experiment with it, play with it, see how it works. But for this, we're going to use the Kademlia DHT. And then again, nothing's changed our transport. So peer discovery, what we've done is we've taken the dial the manual dial from down here. And we've just moved this into our bootstrap list. And so what this would let us do is if I wanted to, let me go look at that dig again. So if I look at dig, if I want to like, hey, let's add EWR, looks like fun. Let's add that. The reason we have to add these individually and not just add the main thing that we did a dig on, the reason for that is currently DNS adder resolution in JS. We don't have that in place yet due to needing to do DNS over HTTP in web browsers. But we can add another bootstrap node to our list. It's no problem. You can add as many as you want. And when the node starts up, it will automatically dial all of this. And then DHT. So we're going to turn it on. And then we're going to enable random walk. Just see these explicitly there. If you add the DHT by default, these will already be in place, but I just want to kind of show you where those options would exist because there are some additional options. You can change the interval, the frequency. You can look at that in the DHT configuration, but this is kind of the base for expanding off of that. And then the rest of this code is all the same. So what we can then do is run 0.6 pub sub because we're doing the previous chapter on discovery. I'm going to run 2 of these. Oh, I did something. What did we do? Oh, libp2p awaits start. Something's broken. Debug. Star. I broke something bad. Oh, huh. So I need to push that update. We need to actually call the main function. It's important to run the code if you want it to work. There we go. I'll push that fix up after this. Sorry about that. So we have our base code here. Discovery's on. Once the DHT kicks in, you're going to see a lot of peers get discovered very quickly. This is what's going on. We're doing the random walk. And then if I run on the other node, we'll connect to those again. This is going to do MDNS. So if we look at our peer ID QMU, we actually discovered that very quickly, actually faster than our bootstrap nodes because we're on the local network. So MDNS discovered really quickly. So we can say, hi there. And we got that there. Hard to see amidst the connection spam, but we have that connection there as well. So this is nice. We're connected to the WebRTC server. We're connected to Bootstrap servers. We queried the network. We walked the DHT. So we're also connected to a bunch of other random peers, either over TCP or WebSockets. So there's a lot going on there. Okay. Yeah. So the dig, if you add the text type, that will give you that dig. I won't dive into implementing your own DHT. That's a lot of work. Oh, hi, you can see my chat. I better close this. I trust you all, but I shouldn't. So I'm going to close that. But yeah, so this is great. You can see you guys actually chatting in here. So you're connected. You're on my robots. So from there, we have discovery in place. Like what next, right? So we've at the point like we can connect to peers. We can discover peers. We were able to chat with one another, which is cool. But again, like we are checking all of our open connections and we're spamming everybody. Like every time we send a message, this is not polite to our neighbors. So how do we make that better? And as we kind of alluded to, this is going to get into PubSub. So there are currently 2 implementations of PubSub, which is GossipSub and FloodSub. GossipSub is widely supported now in the various implementations. There is an update to the protocol 1.1, which is being slowly rolled out. So Go already has it, and then JS and I think Python are working on that, and the other implementations will be working on it soon. And the nice thing about Gossip Sub is if you don't support it, it will actually fall back to Flood Sub. So there's really no reason not to use Gossip Sub. You should totally use it. If your implementation supports it, use it. It's much better. So like, what is PubSub? So PubSub is basically what we do is we create overlays on the network, and I'm going to talk specifically about Gossip Sub because Flood Sub is not much better than what we had before because it floods the network. It will publish to every peer it knows, and a lot of times like we get messages back and it floods. It's very effective at getting data across the network, but it's very bad for the network. What Gossip Sub will do is it will actually develop kind of like handprint meshes over the network. So as more peers join who subscribe to the same topics, it will actually like connect to specific peers and develop a subset. And then those peers will develop their own meshes. So you'll have multiple meshes. They'll communicate messages across one another, and they'll share messages to a subset of peers, not to all of them, just to a few. And the reason it's called Gossip Sub is because like this has an intrinsic like chance of failing to like deliver a message, because like if I'm only communicating to a few peers, like we run the risk of not getting to everybody. So what actually happens is intermittently, Gossip Sub will actually gossip to everybody in its mesh and say, here are the peers I've recently seen. Any peer in its mesh, or like it will also do that to random peers, like Flood Sub like. So it picks mesh peers and non-mesh peers, sends that out and says, I've seen these messages recently. Those peers can then come back and request that message if they missed it. And so this is kind of like if you're familiar with IPFS, this is like bit swap of kind of having that exchange. Like, do you have this thing? I want this thing. Like, this is what Gossip Sub kind of enables us to do to be a bit more polite to the network and only send messages to a select few by still having some guarantee that we're getting messages. So let's switch over and change this out. So what we're going to want to do is we can, again, for the sake of time, I will just pop into the 0.7 messaging session. So what we did is we stripped out our chat protocol. Now what we're doing is we're using this PubSub chat. And very briefly, we'll look at what that is. We'll get into this like this messaging, but it actually uses like a more complex message instead of just streaming data over, because more complex applications will want to use more complex messages. But this is just a basic chat protocol. We won't dive into it too much, but this will go in. It will subscribe to the PubSub topic, which is going to be our chat topic. And then it's going to let us do a few things. Like if you are in the browser version, you can actually do /name and then set your name, because we're doing like a little bit more complex messaging, which we'll walk through in a little bit. But that's basically what it does. And then when we get certain updates, we'll notify our peer about certain changes. Like there's the ability to send like stats of, hey, what type of node am I? Who am I connected to? And this lets us build the edging that we're seeing in the graph that you can see in the browser version. So from there, all we did was we stripped out we don't need the libp2p handle anymore, because we're not running a custom protocol. We're building a custom PubSub handler. And so now what we have is we have this PubSub chat constructor. So we've called that, and then it's going to take libp2p because it's going to bind on top of it. It's going to take the PubSub chat topic, and then it's going to take a handler. And that handler is just going to have, like, we've customized that inside. And so this is what PubSub is going to call back with. It's going to tell us who the message is from, and then what the actual message is. And that message is a struct of information. So we can go through there, and ultimately what we're doing is kind of binding like, okay, who's this message from? we want to update any user handlers, and this is the ability to change your name. When we get that notification, if it's a name change, we'll update that locally. Not the best way to do this in reality, but it just kind of showcases you how to go about doing that. And then again, because we're a node, we're just going to log that out to the console. Yes, so PubSub, are these signed? Yes, all PubSub messages are signed by default. So you know who they came from, they're verified. You can turn signing off if you want to, but it's on by default. Encryption part works in this. So with PubSub encryption, like everything's already encrypted. Like at the very beginning, when we set up encryption, everything that goes over libp2p is encrypted. So these PubSub messages, when you sign that, right? So you're going to send the PubSub messages. What's going to happen is first PubSub, GossipSub is going to sign it and say, okay, this message is from me. Then it's going to fire it to the multiplexer, which is going to prepend any stream data to let the other application know, like, hey, this stream that we've been working on, this message is part of that stream. And then that goes into encryption. And so like everything is unencrypted except right before it's going to leave your machine, we encrypt it. And then that goes across encrypted. The other side, the remote peer, is going to take that, going to decrypt it, run it through the multiplexer, pass that back to PubSub. PubSub's going to look at it. It's going to check the sign. It's going to verify the signature. If that fails, it's just going to throw the message. It's just going to discard it. We don't do any, like, we don't tell you that it worked. We didn't tell you that we discarded it. We just silently get rid of it because we don't want to let you know that that failed for security reasons. And then all we did is we changed our chat input handler so that we are actually running PubSub chat send. So any message that comes in again from the command line, we can just do a PubSub chat send. So if I run that and we are on 0.7, I can hit that. Notice this isn't yet doing the name change. We'll look at that in a second. So if you're trying to do a name change in Node on this version, it won't work yet. But we can get in there and I say, hello, everyone. And so we're getting that information. So we've gone from direct message to now chatting over GossipSub. All right. So the next thing we'll look at is the last thing is really this idea of complex messaging. And so most of the messages you'll see in libp2p are protobuf based, but there's no reason, you don't have to use protobuf. You could use JSON, you could use CBOR, like you can use any serializer that you want to. You could use just strings if you wanted to, but ultimately the thing that you want to use, which is why we use protobuf, is to get the deserialization and to account for size. So you may want to take that into account when you're figuring out serializers to how much data you're actually sending over the wire. That will matter. So if we look at our, we'll just go ahead and look at the messages very quickly. So our messages have a request type, and it's just going to say, okay, this is a message, I'm sending a message, or I'm letting you know that some of my metadata changed for stats. And so from there, we've just got some fields defined. You can see that the type of the message is required because we need to let you know that we're sending something. And then just some additional fields there. So send message, we're including the data, which is the full PubSub message, the full signed PubSub message. And then we have the timestamp of when it was created and the ID of the message, I believe. And then from there, update here, this is just our very crude message for saying like, hey, I've updated my user handle. So now like you can render me whenever I send new chats as that person, and we'll see that in a second. So if I jump back over here, I think the only change we actually need to make, let me check this for to-dos, is right here to change this, not that. Oh my goodness, there we go. All right, so ultimately here, when we get a message from the command line, rather than just sending it, what we want to do is we want to check command. And if we quickly look at check command, I believe this is going to return us a bool. Yeah. So this returns a bool that says, hey, if there was a command, we're just going to return true so that you can know to exit. So when we go pub/sub check command, if that happened, just exit early. Otherwise, we can go through and actually send the message. And so that should be it for setting that up. So if I run O.7 messaging again, and I'll run that again locally here, then I should be able to send messages. Yes, hello. And then I should also be able to change my name. Oh my gosh, this is, let me get rid of all these peer connections for a second so we can actually see this. All right. So we've got that data. And then if I do /name, which you can do also again in the chat above or in the browser chat, we can change our name. And I'm gonna say, hey, it's me. So we see over here, we actually are displaying just a system level notification of like, so-and-so changed their name, like you might see in like Riot or IRC or something. And then if I send a subsequent message, we can see now that that's coming through. So we were able to pass this. So using that same chat protocol, creating a complex message, and then just sending that. So we don't have to have a bunch of protocol handlers. We have one that knows how to handle more complicated data. So we've went through the writing the complex messaging. So we're going to kind of wind things down now. And so really talking about like looking at next steps, right? Because like if we built this chat application right now, we're on the public network, but what happens if we're trying to find nodes that run our chat protocol, like a pub/sub protocol, or who are listening to our pub/sub topic? Like if the network has millions of nodes or billions of nodes publicly, like if you just join and then try to publish something, you're likely not going to find the person on your topic. So how do we broadcast these messages from a set of peers or in millions of the network to kind of get back down, find who we really want to send to? So this kind of brings us back to the Kademlia DHT. So what we're actually able to do is we create provider records, and like again in IPFS, these are content blocks. But you don't have to use it for content blocks. What you can do is you can say, hey, I want to take this pub/sub chat topic that I have. I'm going to turn that into a CID, which is a content identifier. So you would just need to, for us, this would be npm install CIDs is the module. There is a CID module. That's not right. It's CIDs. Unfortunately, the name was taken. But ultimately, what we can do is that we can then take that string of, hey, libp2p chat pub/sub topic, pass it to the CID, and then we can do a find on the network for that, right? So what we might be able to do is we take this libp2p chat protocol, and then whenever we subscribe to the topic, we could, in theory, like query the network and register as a provider to say, hey, I am on this chat topic, just like we provide content, right? I download the content, I'm now a provider, you can come get that from me. So here with the DHT, we could do the same thing. I'm like, hey, if you want to be part of this pub/sub topic, like come connect to me, I'm on this topic. So then anytime we go to like additionally subscribe, we boot up, we can also query the network and ask like, who are providers? Like I want to join this topic. And so we can find those providers that way and then join the pub/sub mesh from there. And then GossipSub we'll take it from there. Once we find peers, GossipSub also incorporates a peer exchange so we can learn about other peers who are also speaking on the topic. So that's a nice way of being able to handle that. And you can do that in a variety of ways. In the future, again, I talked about kind of like rendezvous services, and that's like a federated version of being able to do this. We're going to do that hopefully in the next few months for JS. And the reason for that is like, again, running a DHT in the browser is pretty expensive. So what we want to be able to do is actually use rendezvous servers so that you can register on the rendezvous service, say, hey, I'm a provider of this, or query for those providers. So I'm going to kind of just open it up into questions now. And if I missed a question from before, please go ahead and repost that. Let me check. You set up rules for caching topics and messages that your providers hold a few messages. Yeah, so there's actually in PubSub, there's a recently seen cache. So PubSub already handles this because this is where the like I have comes in. That cache right now is just a least recently used cache. So once you have too many messages in there, it will drop out. But in theory, you could totally fork Gossip Sub or build on top of Gossip Sub, extend it, and then you could build your own cache on top of it. I think 3box, I'm not sure if they still do this, if I'm thinking about the right team, they actually create like cafes. And because like, hey, right now our chat isn't persisted, but what you can actually do is like, we can create that cache, we can create that database so that when you rejoin again, you can get all that data back. And I'm not sure how Matrix is doing that, but I imagine they're doing something similar in terms of being able to exchange that chat. Any other questions? Again, if you guys are working through this and you want to go through the tutorial offhand, please feel free to ping me. Like you can ping me in that GitHub repo, hit me up on Discuss. I will be in the HackFS chat over the duration, so you can also ping me there. And I am more than happy to walk you through this or talk about any more of these like complicated topics. How about robustness in this whole system of protocols if we want better discovery? I'm not sure what you mean there. Could we unmute Siddharth?
Hello?
Yeah.
Actually, I need to know the difference, the pros and the cons of the library P2P.
The pros and the cons? Yeah,
Yes.
so like if you look at the benefit of libp2p is really the peer-to-peer system, like having a decentralized system so that you're not relying on centralized infrastructure. The consequence of that is that it's slower than, in some instances, a lot of instances, it's going to be slower than centralized, right? And centralized is easier. I can spin up a server or a multitude of servers behind like a load balancer, and I can have tons of peers like coming to me and getting that information. The consequence of this, right, is that like you lose, like there's one person who has it. If you've ever been like part of an early adopter of a program or an application, and then they just like, okay, we've run out of money, we can't support this anymore, we shut it down, we shut all the servers down, like all your data's gone, right? Unless they were kind enough to like extract all that for you. So really what libp2p allows you to do is like bring some of that back, make it peer-to-peer so that you're not reliant on these centralized infrastructures that can just shut down at any point in time.
Okay, thank you.
Yep. Any other questions? I'm just perusing for questions.
Yeah, if I know people asked a few things throughout, so if we kind of jumped over it while Jacob was going through his tutorial, feel free to raise that now.
I don't think there was a question earlier around circuit relays that I don't think that we passed over. Trying to find it. A little bit about the circuit and how it might be shared.
Go ahead, Karate.
So the question I asked was when you were setting up a circuit and then sharing that circuit between different peers and basically being able to create multiple connections across that circuit, or then you talked about sharing the connection. So the whole idea of the circuit and what that was. And then all these other questions you can see are transport questions for me, like identification, key exchange, that encryption. And so links are fine. You don't have to answer them all here. I just also want to say I'm grateful, and I want to thank you guys for making this a lot easier than a couple of years ago. So thank you.
Yeah. So for relays, and this is one of the things that we're looking at improving the relay infrastructure. One of the consequences for relays is that they are expensive to host, especially if you're doing something like file exchange with IPFS or Filecoin. Like running a relay is like you're running multiple peers, like file downloads through multiple peers. That's very costly, and so you don't really want to do that. And so one of the things that we're looking at doing is actually building limited relays. And so what they would do is you would be able to kind of rate limit peers and do things like WebRTC peer exchange. Like we could do distributed WebRTC. So rather than using like centralized ICE servers and centralized signaling servers, you could actually find relays on the network via the DHT or some other discovery mechanism. You can connect to those relays, announce yourself. So, hey, I'm listening on this relay, then re-advertise to peers on the network like the DHT or rendezvous servers and say, hey, my new addresses are here. I'm now available at this relay. From there, you can also say, okay, I want to speak WebRTC star because I'm in a browser. So you'd be able to establish the connection over the relay, do a very minimal SDP handshake because that's not a lot of bandwidth. We can do that, negotiate with other peers next to us who have some way of checking like NAT status or giving us SDP offers like decentralized ICE servers. And then we can do a connection upgrade to there. So taking that relay and then do hole punching and then say, okay, I no longer need this relayed connection. Now I'm going to use the direct connection that we were able to just establish. And then from there, we can back off and do file transfer over like WebRTC. But that would also work for anything like coordinating TCP simultaneous handshakes to hole punch TCP connections. So there's a lot there that we're trying to look at, like how can we reduce the cost, because like relays are so very effective at helping with this, but we also want to reduce that cost of like not sending gigabytes of data over relayed peers, because that's not very nice. Did I answer all of your questions? Somewhat. If there's other follow-up, please.
I'll put it in Slack. I'll just put the question. It's about the security stuff, noise, and then SecIO. I'll put it in Slack from
okay. Yeah, and that will be, those connections will be fully encrypted. So while you're actually like sending you're going through an intermediary peer, right? So there's always that concern of eavesdropping. But what you're doing is we have a relay, we have peer A, peer B. Peer A is going to establish a secure connection to the relay. Peer B is also going to do that. And then as part of this negotiation process, these A and B are also going to negotiate fully an encrypted connection over this stream, right? So it's a virtual connection. So while it's running over it, all of that data is encrypted. So like there's no chance, like you can't man in the middle of that. Like it just, it's secure.
Okay. Yeah. Thank you very much.
You bet. Zoom, is video streaming like a Zoom clone built on libp2p possible? Yeah, so I hope I didn't jump over questions I might have.
Yeah, there were two, but go ahead with that one first.
Okay. Yeah, so video streaming you can do. Ultimately, the thing here, right, is to be able to run data channels. And so there are things like, I think there's already somebody working on, not in libp2p, but using WebTorrent to run video streaming. But it's entirely, check out live peer. So it's entirely possible to do that, to run video streaming over that. The big thing there, right, is making sure that you can get that direct connection. And so like WebRTC, you would want to make sure that you're using data channels to send this information. And there are like streaming services that are already using like WebRTC for video conferencing. Talkie is one, I'm forgetting one of the other ones. But these applications where you're able to just open up a browser window and you immediately get end-to-end encryption WebRTC video sharing. And that's all peer-to-peer. Like, granted, there is that initial SDP exchange, so you have some central server, but in theory, that can be entirely done libp2p. Like, you could use, in the future, distributed WebRTC signaling to establish that data channel connection, and then you can stream. Yes, Jitsi, thank you. So Jitsi is the other one that I was thinking about. And sorry for skipping some of these questions. Go back. Can you briefly talk about exchanging streams over libp2p for use cases like live streaming? I think we kind of talked about that. Hopefully I answered your question. If not, feel free to follow up there. From YouTube chat, what level encryption is used when the message leaves the client? So I assume you're talking about the stream encryption, and this is noise or TLS depending on your security transport, right? So all of that data, whether it's pub sub or direct messaging, before it leaves your node, it's getting encrypted with noise or SecIO. And so depending on which protocol you're using, like that could be symmetric or asymmetric encryption. It depends on the transports. And so like those will evolve over time, but you can change those. Like the noise protocol is, the framework's open. We have a spec for the version of it that we've implemented. And so you can actually go look at the spec, see what's going on in there, look at the encryption patterns there. But yeah, it really depends on what version of crypto you're using. Is libp2p, I think this is the next one, libp2p on mobile phone doable? An existing team working on that already. There are a few people working on it. Textile is actually working on, they have some versions of Android and iOS for Textile. So that's like, I think IPFS Lite. So it doesn't bring everything that IPFS brings, but it has like some portion of IPFS, and then that's running libp2p. So it is possible. There's like a Java implementation, which you'd be able to use with Android. And then for JS libp2p, what we're working on is better support for React Native, because there are some folks who are going to be building more React Native apps. So the big thing there is really, again, hooking up the libp2p itself, bundling that in React isn't too big of a deal. We just have to get past like the JavaScript locals and then hook into like writing those custom transport or those transport bridges to get TCP or UDP from the phone itself, from mobile itself. And so that's really what we're looking at now, is like, how do you bridge the transport of those modules? Do you prefer to use member list technique more than libp2p during implementation file exchange? Could you, I'm not sure what you mean there, if you could expand on that. Elmo?
Hello?
Yes.
Okay. Yeah. Now I have the member list technique.
Mm-hmm.
It's against the library P2P. It's more fast than library P2P, but maybe it's not secure more than the library P2P. So I need to know more from you, more details about the I need to more information and details about the security in the library P2P.
Okay. I will try to answer this as best I can. Memberless technique. Are you talking more about like permissioning for file exchange?
It's not. It's a secure channel.
Mm-hmm. So, okay. Well, so like all communication in libp2p is secure. So really the question is like, do you want your application to be on the public network? Oftentimes this just isn't the case. Like you might want to do kind of, there's a couple things you can do. You can run private networks that don't connect to the public network at all. You can also encrypt those if you want with, in libp2p, by default, we have support for symmetric private network keys. So you can actually add a pre-shared key to your swarm, and everything that goes over the wire, like there's no leak of multi-stream or anything, everything that goes over the wire is encrypted with that private shared key. So you can ensure no one on your network is able to talk to a public node, and no public node is able to talk to your network. So as long as those pre-shared keys don't get shared publicly, like you can encrypt that entire network. If you're less concerned about like, okay, I'm okay being open to the network, but I really don't want to join the public network, but I want people to be able to find me. This is where you kind of get into some things that we've been looking at with the DHT of doing like running multiple DHTs. So in the future, we'll probably look at libp2p being able to run multiple DHTs. So what you'd be able to do is like, okay, for our application, we're going to run a DHT just for us. And then we're also going to run a DHT on the public so that people can find our application. You join the public network, figure out, okay, I want to join libp or this app. So then I can find peers who support that and then join that network and mesh in. So this is kind of like, and this is really where I think the peer-to-peer network like should evolve over time, is being able to like, I want to join the public network, and from there, I want to find the peers that I care about and connect to them. Like for like network security on universities and things like that, like doing like full network privacy, like encryption, like that's a lot more valuable. But if you want to be able to at least kind of stay public, then that's probably the way to go, is isolate those DHTs.
Okay, thank you.
Yep. What is the major difference between libp2p implementation on IPFS versus on Ethereum? So they're not really that different. So ultimately, the biggest things, the big differences there are what's built on top of them. So like I talked about at the beginning, like disk v5 discovery, that's the discovery mechanism that Ethereum uses to join the Ethereum network. And it's not necessarily restrictive, right? Like you could build an app on JSLib2p to connect to Ethereum and get the modules and connect to the right place. For JavaScript, ChainSafe has a Lodestar, which is a client for Ethereum, and the other implementations have various versions of Ethereum clients, but these are all built based on libp2p. So like noise is the same. They might use different versions of DHTs, like might bring their own DHTs. So that's really it. The core of libp2p doesn't really change, and that's why like libp2p, like we are driven by you guys wanting to do things, whether it's on IPFS or Ethereum or anywhere else. Like that's what we're trying to solve. Like we didn't build originally. libp2p actually came bundled in IPFS, and when we built JS, we actually built libp2p separately, and then we ripped the Go version out of IPFS because like this is a protocol that's valuable to anybody building on public networks. So that's ultimately what we wanted to do, and we've been working with the Ethereum community to make sure libp2p works for their needs.
I think that might be it. And we're definitely well over time, so I'm gonna wrap it there. No, it's not you. This is all great, but we should probably not make this a 2-hour video.
Yeah.
That was really great. I'm glad people got to follow along and see your process for all that. There were some people asking about where they could actually find the repo for this. Is that just a link to the README you had earlier?
Yeah, I just need, let me pull that up.
Yeah, I guess you could just drop it in the Slack channel. And that's probably the best place to find it if people are still looking for it. All right, with that, I think we can wrap. Thank you again, Jacob, for sharing some of your knowledge and the work you've done. Much appreciated. We got to get more people to, this is the constant issue. Nobody wants to put on their video, so it looks like there's only 4 people here, but we had 50 earlier, and it looks like 30 people stuck it out to the end. So good job, folks. Oh, there's Andrew. Andrew's jumping back in. Give the golf clap.
Yeah, that was years of me reading stuff that he just compressed into 2 hours. Yeah, that he saved us all a lot of trouble.
It's like time travel.
Yeah. Yeah.
Yeah, again, thank you, Jacob. And like I mentioned, he'll be available in the Slack with links and additional feedback as we move into the actual building part of HackFS, which consequently starts Monday or after the kickoff at 12 noon. I believe the actual hacking kickoff is at 1:30 p.m. Eastern. So that's when everybody can open their repos and start hacking. I think that's it. If you haven't staked, make sure to stake. We've got one more event, like I mentioned, the brainstorm session with Juan tonight, and hopefully we're going to wrangle a couple more people. It's going to be fun tonight at 8 p.m. Eastern. And I think with that, we can wrap. Thank you, everybody. See you in Slack.
Thanks, everybody. Bye.